everyone, welcome to 365. We are moving quick in this class. We're moving on to assembly crash course. Obviously, the recitation's still available. You have questions about Talking Web, show up to recitation, ask questions on the Discord. The module is still active. As a reminder, it is due, let's see here. It is due in 4 days, 11 hours, and 55 minutes. So you still got plenty of time on Talking Web, but because this course moves quick and the next module takes a lot more, I guess, of a bootstrapping process to understanding, we are moving on ahead to talking about it. So this assignment has already launched and it is due in 13 days. So you kind of have two simultaneous assignments. That way, if you've already finished up Talking Web, you get to move ahead, continue on at your own pace. But both assignments are currently active, and we will be talking about Assembly Crash Course. So for reference, how many people here have taken 230, CSE 230? Okay. And it's still the case that everyone is like learning MIPS, right? This is the language. They're not doing x86 yet? No, okay, no one says x86. How many people are currently in 230, like this semester? Okay, so a lot of people. If you are not taking 230 or not in 230, fortunate slight disadvantage, but it's a different language. We're doing x86 64. Same kind of concept as MIPS. It's an assembly language. It's kind of like operate, do this instruction, this instruction, this instruction. But some of the behavior works a little bit differently. And the reason we're talking about it is because this is the language that maybe not all processors, but a whole bunch of processors run. ARM is increasingly becoming more popular. So there's a chance your laptop right now is running ARM instead of x86, but a lot of people are running x86, and the pwn.college server is running x86. Okay, so that is what we're going to be talking about. Okay, so I have set up a little bit of an environment, and the way that we're going to do this is we're not going to use slides for this lecture. We're just going to like demo how stuff actually works, and we're going to use a debugger to show how those things work. So who here has used GDB before? Okay, some amount of people. Awesome. Okay, so we are talking about x86 64, and if you want to start writing an x86 64 program, this is the basic skeleton here. This shows up? Yeah, it looks like it shows up. Okay, this is the basic skeleton. So maybe you've written Java before, right? And you have public, static, void, main. It's honestly been years since I wrote Java, so I don't even know. I don't know. Maybe there's stuff in there. That's the skeleton there, or you have a C program. You have this boilerplate here. Oops. And you write your program, there's boilerplate. Every language has some amount of boilerplate, unfortunately. The boilerplate for assembly exists as well. It's a bunch of words that realistically you don't really need to seek to understand, but I'm going to explain them anyways real quick, just because they're here, so you're probably wondering what the heck these words are. So the very first line says Intel syntax, no prefix. All this is saying is that the assembly we're about to be writing is using the Intel style as opposed to the AT&T style of syntax. We like the Intel syntax, so we tell our assembler, hey, we're going to be using Intel syntax. No prefix just further makes the syntax simpler. So this is just saying, hey, this is what my syntax is going to look like. This global that's like missing an A or whatever underscore start thing, this is saying I have some symbol in my program. Maybe you could kind of think about this if you've hopefully written C before. If you do like int func boom, and then you do int func, right? You like pre-declare something, and then you actually go on and define it or whatever. Global works kind of similarly. It's basically saying I have this underscore start symbol, and I'm going to expose this thing in my elf file. We'll talk about elf files later on. But we're going to expose this thing. And then this label / symbol here is underscore start. So that's the thing that we said, hey, expose this thing. This is that thing that we're exposing. And the program, when it runs, is just going to automatically start at underscore start. So you've written a C program, you've defined main before, things just start running at main. Underscore start is the thing that things just start running at in assembly. Okay, so let's demonstrate this. So I also set up a makefile. Doesn't really matter. Basically, what we're going to do is we're going to assemble this thing. So we're taking this file here, which I've called test.s. Test.s, we're going to assemble it, which is going to produce test.o. And then we're going to link that thing, which doesn't really matter here. I mean, it matters to make it so that it can run. But you can kind of think of the assembling step and the linking step as we're building this thing right now. So we're linking this test.o and we're producing test. So suddenly we have this test file. So similar to when you run GCC on test.c and you produce the test binary and you can suddenly run this test binary, this is our test binary. We can run this thing. Okay, so we have our test.s. We will make test. So we'll make clean, make test. So this assembled it, it linked it. Now we have this test.o file. We have this test file. All we really care about here is this test file, and we can run it. So this program is not going to be very exciting when we run it. We haven't really written much of a program. But when we run it, we segmentation fault core dumped. Who here has seen segmentation fault core dumped before? Is this like a new message? All right, it's a new message. What this means is that the program crashed. The program crashed, and the reason it crashed is that it accessed memory that the program doesn't have access to or doesn't have the permission to access. And you might say, why did it access memory that it doesn't have permission to access? Well, what happens here is this nop instruction runs, and we're going to show that this nop instruction runs here in a second. This nop instruction runs, and then something is after it. There's some amount of instructions, and we're going to see what these instructions look like. But this instruction runs, and then let's pretend here, we have another nop instruction, this nop instruction, and then like something is here, even though we haven't defined that something. This instruction runs. Nop means do nothing. It's a no-op, so it literally just says do nothing, do nothing, do nothing. So we do nothing 3 times in a row, and we're dealing with an actual CPU. There's real memory. Something is here in memory, even though we didn't explicitly say what those things are. Whatever that is, our program hit that. And the way that it turns out null bytes are interpreted, you very quickly and very often run into a segmentation fault. We'll see why as we go along with this. And the program just crashes. So your program does not automatically exit. You write your int main, right? This would be the equivalent of the do nothing program, but this program doesn't crash. The reason for that is that the C runtime calls into main, and then once main is done, there's an implicit return statement here. It returns back into the C runtime. The C runtime exits the program cleanly. It does that all for you. We don't have that. We are literally just writing instructions that your CPU will actually be executing, and we'll get to this later on as well. There's a lot to cover. We didn't call a system call to exit the program. We never cleanly exited. Okay. So let's go ahead and show that this program can run and what it looks like for this to run. So I set up this makefile, and what we're doing with this makefile is we're launching GDB. So the core of this is GDB test. So we're running the test program under GDB. I make it so that GDB is more quiet. And then I also am using this debug.gdb GDB script. Doesn't really matter. It's going to make it so it's easier for us to see what's going on as we execute this program. If you're curious about the specifics, I can link it on Discord or something after the fact, but this doesn't really matter here. Okay, so we're going to finally type make. So here is how this GDB script has been set up. GDB is a popular debugger. It lets you start single-stepping through instructions. You can start looking at memory. You can start looking at registers. So there's this thing called a register. If you haven't heard of a thing called a register, we will briefly introduce it. The way that I have this configured is to show a basic minimal amount of stuff. So you can see up here at the top, we have our _start symbol. And you can see that this arrow is saying, hey, the next thing we're going to execute is this NOP instruction. Then we'll execute this one, then we'll execute this one. We'll see that. This NOP instruction is loaded somewhere in memory. So your computer, your server, your whatever, has a huge region of memory, right? Hopefully everyone has heard of memory before. You have this huge sequential region of memory, and all of these instructions are living in memory. This very first NOP instruction lives at the hexadecimal address 401000. The next one is at +1, the next one is at +2. Right? So these three instructions, each instruction takes 1 byte, in this case, for these NOP instructions, and they're just sequentially in order in memory. We just have a NOP instruction, a NOP instruction, a NOP instruction. Okay. Now, the next thing that I'm displaying to you is a handful of the registers. So a register is just this thing that can hold 64 bits. That's all there is to it. A register holds 64 bits of information, 8 bytes. An x86 64 with these R prefixed registers. We'll talk about some of the mini versions of these registers, but these R prefixed registers all can hold 64 bits of information. That's it. So if you wanted to store the string, hello, my name is Connor, you can't store that in 64 bits of information. That could not go in a register. Fortunately, though, we have this massive thing of memory. And right now, we're just showing you 64 bytes of memory. Specifically, we're showing you memory here that's on the stack. We're representing this memory as 8 bytes. So this is 8 individual bytes. You can see all 64 of them are currently null. And then we're also representing what these 8 bytes are if interpreted as a 64-bit integer as well. So this integer thing over here on the right, prefixed with 0x, hexadecimal, versus these 8 individual bytes, these are corresponding to the same thing. And these things are located at 7FFFFFFFFF E2D8, right? So this is just somewhere in memory, sequential memory, just a huge chunk of memory. At this location in memory is 8 null bytes. 8 bytes further, there's another 8 bytes, right? So that you can see that this is 2D8, 2D0, 2C8, and so we're counting down really is what we're doing here. So we're just keep subtracting 8 from the previous, so 2D8, 2D0, 2C8, 2C0, 64 bytes worth of memory, that's what we're showing to you here, and everything starts out nulled out. Is there any questions about this, this initial view of everything? Does anything not make sense? All right, good. I mean, if things don't make sense, that's also okay. Let me know. But hopefully it's clear. Okay, so this program and the way GDB is a language in and of itself, unfortunately, it's kind of gets complex, but we're going to kind of do an overview of it as we demonstrate this as well at the same time. GDB has a little prompt here just waiting for some sort of command to instruct it, how do I want to use the debugger? And what I have typed in here now is SI. SI stands for step instruction. That means go forward 1 instruction. So I'm going to hit SI and I'm going to hit enter. And you're going to see that now our fun little arrow thing is pointing at the next instruction. What that means is this instruction right here, executed. The next instruction to be executed is now this guy. You can see that one value in our registers, one of these 64-bit values, this thing is called RIP. RIP points at the next to execute instruction. So maybe you've heard of like a program counter or PC. What's it called in MIPS? Is it PC? Yeah, it looks like it's PC. I think it's PC. It's the program counter. And you'll see that before it was pointed at this value. Now it's red. That signifies that it changed. Now it's pointing at this value. So it's just pointing at the next thing, 401001. It's pointing there. We hit SI again. Guess what? RIP goes up again. We're just stepping sequentially through instructions. So for our purposes right now, and we'll get to the case when this is not true, instructions just go to the next one. Just to the next one in sequential memory, we execute the next instruction. So just for our purposes here, we just keep adding 1 to the RIP. we'll see that not all instructions are the same size, and in fact, there's a whole bunch of sizes for instructions. It just increments by the size of the instruction to go to the next instruction, and then that gets executed, and then that gets executed, and so on. So we're going to SI one more time because probably naturally is like, why are we crashing? So I hit SI, and you see that this changed up here. The reason it changed up here is because the way that I'm like disassembling it to show the assembly. I mean, there's nothing to show anymore. There's nothing left. Here's what's next in memory. And this maybe is a terrifying looking instruction. By the end of today, this will not be a terrifying looking instruction. But what this instruction is actually, if I print, let's say 8 bytes of memory at the instruction pointer, you'll see that right here in memory at 401003, so before it was 00, 01, 02, now we're at 03, is just a whole bunch of null bytes. And it turns out that null bytes, 2 null bytes in a row, because you can see, right, this is 3, then 5, then 7, 2 null bytes in a row decode for this crazy instruction. Trust me, it's not a crazy instruction. We'll get there. And this instruction here is why our program crashes. It turns out you can't do this. And the program crashes and it's done. So that's why it says segmentation fault. Turns out it's accessing memory that cannot be accessed. So I hit SI, you have to actually type it again, and the program terminated with signal seg v segmentation fault. Program no longer exists. It just crashed on that instruction. Okay. So now let's write a program that does something slightly more interesting than the do nothing program, really the crash program. So what we're going to do is we're going to look at these registers. Before we get and deal with memory, let's start with registers, make sure we're all on the same page about how these 64-bit values work. If we jump back into test.s, and I'm going to get rid of the first 2 NOP instructions, we're going to leave 1, just makes the display a little bit nicer. What we're going to do is we're going to make RAX be some value. So at the beginning, it's just 64 0 bits or integer 0, right? And what we can do here is we can set it. And the way that we set it, the syntax for setting RAX to some value is this. So if I set RAX to hex 42, the set RAX to hex 42 instruction is move RAX hex 42. And this is going to move the value hex 42 into the RAX register. So this is the ordering. Maybe right now the ordering seems confusing. You might be like, why is it not this or something, right? Move 42 into RAX. Well, it turns out it's actually, once you get used to it, this style makes more sense. Just take my word for it for now. The way you can interpret it is move into RAX hex 42. So let's just quickly run that, make sure we all agree that that works. So this program here, if I step 1 instruction, guess what? Now RAX has the value hex 42 in it. And as a reminder, right, in this case, we're looking a lot at hexadecimal values. If I just put 42 here, it's going to put decimal 42 in. And decimal 42 is hex 2a, so just make sure you pay attention to hex stuff when it might be relevant, you know. In fact, it is very relevant. They're different values. Okay, so this is how we can set a register to be some value, right? So in the land of C, you know, this is like int a equals hex 42 or something, right? This is the same idea. You need to be able to assign. Now, unlike C, we have a set number of registers. Right now we're displaying these, and you'll notice that RIP is kind of like already in use. You're not able to actually use RIP. So for example, if I do move RIP 42, it's going to tell me unsupported instruction move. It's kind of like a bad error message. Unfortunately, you'll see that the assembler produces sometimes confusing error messages, right? What do you mean unsupported instruction move? Move is obviously an instruction. We just showed that it's an instruction. This structure here is unsupported. So moving into RIP, there's no, you think about your physical CPU. As we said before, if you have 2 null bytes in a row, that decodes for that weird crashing instruction. there's no representation of bits in a row to decode for this instruction, and the assembler says, hey, that doesn't exist. Okay. So this is assignment, and as we just said, there's a finite number of these things. In the world of C, you'll learn very quickly, especially once we get into like the reverse engineering module in a few modules, you'll learn very quickly that the way that C is able to have like infinitely many variables, right? We could just keep doing this forever, and C is not going to complain about, hey, you can have only so many temporary variables. The way that works is that C ends up taking advantage of memory. So it just starts dumping these values to memory, and you'll learn very quickly that registers are very fast access. Memory is fast, but way less fast than registers. And the way that a lot of programs will be written is that you'll start taking some value, putting it into memory, pulling it back into a register, and you'll just keep doing this hop between memory and register. And the reason for that is that most instructions can only operate really on registers. Now, there's a whole bunch that can also operate on memory, but in general, registers are critical. So, for example, let's write a program that is move RAX42, move RBX hex 1, and then we'll show another instruction, yet another instruction. Let's do something other than just set values. What we can do here is add RAX RBX. So what this is going to do, probably it's very clear looking at this, if we've seen the style of the prior instructions, what this is going to do is it's going to add RAX and RBX together. Now, where is it storing the result? Fortunately, I don't remember MIPS well enough. Do you specify 3 registers in MIPS? Yeah, so you specify 3 registers in MIPS. You don't specify 3 registers in x86-64. Turns out the result just goes into this guy right here, the very first one. So similar to how the move, the 42 goes here, the result goes into this first register. So let's go ahead and make sure that we're not making stuff up. So we take 42, put that into RAX. Remember, every time RIP is also changing because we're going to the next instruction. We put 1 into RBX, and now we're going to add RAX RBX, and you'll see that RAX is now hex 43. So this is, right, a very simple program. In the same way that, just to keep it nice and simple, if we said A equals, really A plus equals B, right? It's really basically what we did here. Or if you're scared of plus equals A plus B. That's the program we just wrote. Okay, so that is registers. Does everything make make sense, right? These registers, they hold 64 bits. I guess let's quickly show what happens when we run out of 64 bits. So let's say we move into RAX the value 1, 2, 3, 4, 5, 6, 7, 8. Right, so we are doing 64 bits where each of those individual bits is a 1. This is the maximum possible 64-bit unsigned value. Alternatively, if you think about 2's complement, this is the actually no, it's not the smallest value. This is -1 if you look at this as a signed value using 2's complement. It's kind of in the eye of the beholder whether this is -1 or maximum positive integer. Either way, it's just 64 1 bits on. What happens when we add 1 to this? So we load up RAX, all 1 bits, and we move into RBX the value 1. We add. What happens? It wraps around. It's a ring. It's a modulus, right? It just goes back to the beginning, and it'll just keep looping around this ring when you overflow, right? In some sense, you could kind of think that the 65th bit just became a 1, but unfortunately, the 65th bit does not exist, so it's gone. And that's what happens, so now we're back at 0. So this is called an integer overflow. We're actually not going to get too much into integer overflows in this class. Maybe near the end, actually. But there are security consequences of it, but we're not super hammering in on security right now. But you can imagine how a value suddenly being a really high value and then suddenly becoming 0 could be alarming. Okay. So let's go ahead now that we've seen registers, we've added, we've set them. I guess one other thing to show is that we could do move RBX, RAX. So you don't just have to do immediate values. You can also move registers into registers. So we do that, right, as you expect. It just moves. Wait, what happened there? Yeah, as we expect. Yeah, moves all Fs into RBX, and that works as well. Okay, so we see registers, and right now these registers aren't interacting with memory at all. So let's interact with memory. How do we interact with memory? The way that we interact with memory here, and there's a whole bunch of different styles or ways that we might interact with memory. But for now, we're going to use this chunk of memory. So let's take this nice address right here, 7FFFFE2C0, and let's go ahead and move that into RAX. So in the same way that we moved hex42 into RAX, this is just a value. It happens to correspond with mapped memory, but it's just a value. We put it into RAX. Let's go ahead now and move into RBX, hex42. And now if we want to assign hex42 to this location in memory, the syntax for that is this. It's actually surprisingly not so bad. It's move square brackets RAX, comma RBX. This is the syntax for moving into memory. So the square bracket really just means treat this as a memory location. I'll put it there like it's memory. And fortunately, this thing is mapped. We'll see what happens if this thing isn't mapped, what will happen. But right now, we're pretty good. This is mapped. So let's go ahead and run this program. So we step, and then we step. So we kind of load up our address that we're going to go to. We load up the value we want to write there. And then we step one more time. And guess what? We wrote to memory. So now we have the integer value hex42. Maybe surprising to you is that this 42 exists in memory right at this location. You might think that the 42 should exist at the far right location. The reason for that has to do with something called endianness. Who here has heard of endianness? Endianness is a concept you've heard of? Okay, awesome. x86-64 is little endian. So that means that the least significant byte is first. So we put 42 here, and then of course the rest of them were zeros, so it's not that interesting. Here's maybe an example that will be more surprising to you when I say, pay attention to endianness. Let's write the value 1234, right? Hex 1234. So I don't know if you're expecting to see 12 and then 34 right here, or if you think it should be 34 over here and 12 over here, or what's going on in your head for what you're expecting to see here. But this is what happens with little endian integers. It goes 3412. The reason for that is that 34 is the least significant byte. It's the smallest value if you were like to break apart this integer. 34 is smaller than the 12 in terms of like where it is in the order of the number, right? So the least significant integer or least significant byte goes first. And then the next least significant all the way to the most significant. This is little endian integers. Maybe it seems simple enough. You might be thinking, okay, this is weird, but we'll just roll with it. This sort of thing will come back to haunt you. You will forget about the fact that things are little endian. I'm telling you now, when things are breaking, think about endianness, because this will be an issue many of you run into. Okay, so this is a little endian integer now stored in memory. Now, so we've kind of covered instructions happen sequentially. Also, I guess I said before that all those NOP instructions at the very beginning of all this, all those NOP instructions took 1 byte. You'll see that this instruction right here takes 10 bytes to represent, right? Because it's first we're at +0 and then we're at +10. This thing takes 10 bytes to represent. Maybe it's not a shock to you that you cannot represent some instruction that has like this 8-byte value in it in 1 byte. But so this value here, this is 8 bytes worth of information. And then it turns out the rest of the instruction is 2 bytes of information, like the move into RAX part of the instruction. If we wanted to, we could look at this instruction. So if we could do x/10bx, which means dereference memory, show me 10b bytes in hexadecimal. I know GDB, it's like I said at the beginning, it's a language of itself, but this is how we're going to print 10 values at this location. This right here, you'll see hex 48, B8, C0, and then hopefully, right, we see C0 is right here. Well, guess what? C0 is in the instruction encoding. E2 is in the instruction encoding. Again, as a little endian integer, and then FF, 7F. So this, and then also don't forget these 2 null bytes. There's also 2 null bytes because this thing right here has 2 null bytes in it, right? But whether you want to think about the 2 null bytes or not is, again, it's an eye of the beholder. Is this 8 bytes of information? Is this just an integer that can go up to 64 bits? Kind of, how do you want to interpret it? Turns out, though, it is 64 bits of information. Okay, so this is, and I guess I'll also point out, I don't remember in 230, do you have to like decode instructions by hand or something? Yeah, we're not going to do that in this class. You're not going to be decoding instructions by hand. You'll maybe notice that there's a whole bunch of these like hex 48 bytes if you just like pay attention and look at memory. We don't really care about decoding it. This hex 48 byte within it encodes and decodes very similarly to MIPS. If I remember right, MIPS is always 4 bytes though. This has a more complicated encoding decoding structure, but in the same way that certain bits of information are represented in different parts of the instruction, that's what's going on here. This hex 48 byte is actually a prefix byte that says we're working in 64-bit land for doing this move. We're doing a 64-bit move. So when I say that, let's look at what it means to do something that isn't 64 bits. So 64 bits, we know it's 64 bits because these registers start with an R. Turns out, though, that if we take this instruction right here, so let's say, how do I want to write this? 0x, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I believe that should be good, right? Let's go ahead and do that instruction. Oops. Right, we load that into this register. It turns out that there is also a 32-bit subsection of this register. The name of that register, and temporarily I'm going to put this into RBX instead. The name of that register is EAX. So EAX, so maybe we'll actually put RAX back. If instead what we do is write 1, 2, well, let's see here, how to convince you that this is true. We'll just do that anyways. EAX is just a 32-bit subsection of RAX. So when we do this, so initially we loaded up RAX with this 64-bit value. Now we're loading up EAX with a 32-bit value. And when we step, we're going to see that this whole thing gets wiped away. Even though we moved into something that has a different name, it's not RAX, we moved into EAX, turns out it still affects the RAX register because this is just the least 32 bits of RAX. So if we want to continue down the chain to go to a 16-bit subsection of it, turns out it is called AX. And I guess we'll be kind of correct here that that goes that far. 0, 1, 2, 3, that goes this far. So this is a 16-bit subsection. And actually, I'm going to make this FFFF, and you'll see why. This what I'm about to show is maybe very unintuitive, but it is unfortunately a reality. So we load up the whole 64-bit value into RAX. Then we load up the 32-bit subsection, and we'll see, right, that it wiped away these upper 32 bits. These upper 32 bits became 0. To confuse you, when I step to this next instruction, bits 16 through 32, unfortunately, are not going to get wiped away. It is only messing with those. So it turns out that this has to do with compatibility, or at least that's my best explanation I've heard of this. Maybe you remember when the world was almost entirely 32-bit and like we were just on the cusp of like 64-bit becoming a thing. Maybe you remember that, maybe you don't. I don't know where that age gap lies, but it's very close to around your age. The world was 32-bit for forever, and suddenly we decided we need 64 bits. We need to upgrade all of our architectures to support 64 bits so that we can do 64-bit things. Turns out by upgrading to 64 bits, you have more addressable memory because this address thing can now be 64 bits instead of 32 bits. That's a lot more memory. It's one of the primary drivers for that. They decided that because we have all these programs living around in 32-bit land, that when you might have a program that never touches 64-bit land. It only just does like EAX and never does RAX. They decided for compatibility reasons that we should just wipe out the upper half. That way, when we're moving into like EAX, we kind of are moving a 64-bit value-ish, except the 32 bits are required to be all zeros. And that's kind of maybe my best explanation of why this behavior is different. So why EAX actually wipes out those 32 bits, whereas AX does not wipe them out. Maybe it's confusing. It's just a reality. So this is something also to pay attention to. The only one that does this is this like RAX EAX boundary. If we do AL, so that I guess I'm jumping ahead, the next value is AL. We'll do 1, 1. So this is the all 64 bits. This is the least 32. This is the least 16. This is the least 8. And if we run this, so we have 1, 2, 3, 4, 5, 6, 7. Now these 16 bits get turned into FFs while we're retaining this. And again, if we do this, now just these 8 bits are changed. So like these are all interacting with each other without zeroing stuff out. So this is multiple register sizes encoded within the same register. I've very rarely seen it come up, but technically there's also move AH, which is bits 8 through 16. Probably won't be relevant, but I figured I'll just throw it in real quick. AH also exists. You could do move AH 2, 2 or something, and we will step through. And guess what? These bits right here just got changed. AH doesn't really matter. Technically, some programs use it for, I don't know, I'm sure there's some sort of optimization reason to sometimes use it. But that is the subsections of the registers. You don't need to know or memorize these names. Hopefully, as you kind of do more of this, it'll become intuitive that R means 64-bit, E means 32. Get rid of it, but keep the X's 16 bits. The L is the lower half. This is the higher half of the extended A register, right? So this is like extended A, lower half, higher half. I guess this is probably E is extended. Extended, and then I don't know, R is maybe really extended. I don't know what the letters actually represent there. But that is how this works. So one more thing that I want to point out here is, so we previously showed writing to memory, and we did that by taking some address. And then what we did is move RAX. Actually, we'll move RBX. 0x42, and we'll do that, right? So we run this program. Suddenly we wrote 42 to memory. If you look back up at how GDB is showing these instructions to you, you'll see it doesn't exactly line up with what I wrote. This very first one is called move abs. I think it's like move absolute. And this one right here that deals with memory is move keyword pointer. So keyword pointer as in the thing you've used in C before, a pointer. It's a pointer to memory. Keyword means 64-bit value. So it's a quad word. A word is 16 bits of data. A double word is 32 bits of data. A quad word is 64 bits of data. Why go off of words instead of like bytes or something and confuse everyone? Why do we need a quad thing somehow meaning 64 bits? I don't know. For some reason, historical reasons, not sure. That is the naming convention. So we've got this thing called a word. In your head, if you're ever confused, just think word means 16 bits. That's basically, when you see this, just think that. And quad means 4 of those things. Cool. So we could also write this instruction just like this. So we could write keyword pointer. Caps don't really matter. The same thing. And the reason that this matters, so right here, by doing this instruction right here, we know that what we're talking about is moving 64 bits of data, which means treat this as a keyword pointer because we know we're about to be moving a 64-bit value in because guess what? RBX is a 64-bit value. If I do EBX instead, this is now no longer a keyword pointer. It is a D word pointer, a double word pointer. Because we can infer from EBX that we're talking about 32 bits of information. What if, and something to keep in mind, this might look kind of like a natural way that you might want to express. I don't want to do this whole like preloading registers nonsense. I just want to move 42 in. This is like maybe a natural thing that might feel right to write. It turns out that this instruction does exist, right? Or I guess we haven't seen yet that it exists. But this is not the way that you can type that. It says error ambiguous operand size for move. We don't know what the heck this thing is. Is this an 8-bit value, a 16-bit value, a 32-bit value, a 64-bit value? Maybe you say like, oh, everything above is like 0, so obviously it's an 8-bit value. But like, are you going to say that that's different from the other thing? Like, probably not. It's ambiguous. So that's where this comes in. We can write keyword pointer, and this means specifically that this value right here is 64 bits. So this instruction does exist. You'll notice that certain instructions that you think should exist, like it feels like very natural to just like type it, there's no encoding for it. It just doesn't exist. This does exist. But as we saw before, like move REX RIP, maybe that feels like a natural thing I should be able to write. Maybe I want to like save the instruction pointer off to a register. That does not exist. It's unsupported instruction move that just, and it's not like we syntactically wrote something wrong. This just doesn't exist in the architecture. So the architecture has a definition to it. There are specific things that exist. Even if something feels natural, doesn't mean it exists. Okay. But most things do exist that would make sense. I will say, though, that something that does not exist, so speaking of things that don't exist, let's imagine that we load up 2 addresses of memory, and I want to do a memory transfer. I want to move from B0 to D0. Now, currently it's all null bytes, so it's maybe not all that interesting. But maybe I say I want to be able to do that. So we're going to write this because that feels like the natural way to express that. Unfortunately, this is actually kind of a good error message. Too many memory references for move. I am not aware of any instructions that allow you to access 2 different regions of memory at the same time within the same instruction. As far as I'm aware, there are only instructions for accessing 1 location in memory at a time. So this doesn't exist. This doesn't exist. Doesn't exist. You get 1. So what you do is, and maybe we'll preload into memory. So we'll say move RBX, actually move RCX 1, 2, move RCX 1, 2. We're going to follow a quick pattern here. Move RAX. Actually, we'll put these up here. So we're going to load in to RAX a memory location. We're going to load into RBX a memory location. We're going to put a value in. So we're going to say move into RAX RCX, move into RCX FF, move into RBX RCX, right? Hopefully it's clear what we're trying to express here. Maybe you would order these differently to make more sense of it in your mind. These are two locations in memory. We're using RCX as this temporary placeholder thing, and we're loading into memory this and this. I guess we said before, though, that we could do this, which is actually very valid. If you're thinking that, you can express that. So maybe we do that instead. Both would work. And then, so let's just do that real quick so that we have some amount of data loaded into memory. Oh, something's saying it doesn't like it. Oh, remember what I said? Keyword pointer. Keyword pointer. And then we're going to do that. So we load up our memory addresses. We store 1, 2 there. We store FF there. And then maybe what we want to do, so maybe this happened earlier on in our code, right? We're thinking maybe more abstractly that somehow our environment got set up to this state of existence. And now what we want to do is I want to add together this location in memory and this location in memory. So as we said before, this does not work, unfortunately. Keyword pointer, RBX, right? Maybe we want to add them together and put them into this location in memory. Oops. Well, yeah, it doesn't exist. You can't do that. Fortunately, though, as I was kind of illuminating before, if we wanted to express this concept, the way that we do that is that we need to pull out of RBX into some temporary value. Make sure that you do not clobber your registers. A very nice thing in C is that you can have unlimited local variables. You have a limited number of registers, and it is very easy to accidentally say, oh, I need a temporary register. Let me go ahead and use RAX because I need some temporary register. Well, we're about to do an add with RAX, and we meant to reference this value right here, and we're about to do this. This is not good. What we need is a new temporary register. You have to keep track of registers in your head. This is, in fact, one of the main reasons that C was written, is so that people didn't have to do this register accounting for. It's a nice high-level abstraction. But unfortunately for you, we're working with assembly here because we need to be able to understand assembly. And then we do this, right? So we kind of break it apart from this we break it into 2 instructions. We use this temporary thing, we add it in, and now let's see. I'm assuming that this instruction that you can add straight into memory, and it looks like no one complained, so I thought that was a natural way of expressing it. If we had to, we could use 2 temporary registers and do it, but it looks like this instruction does in fact exist. So we load up memory, we temporarily pull out of memory from this RBX location, so we can see when we execute this, RCX suddenly has this FF value that we pulled out of memory from here. And then we're going to add that here. And guess what? Now we have this value here in memory, right? So we're just like moving into registers, moving into memory, adding stuff. Maybe not so exciting, but this is the basic flow of assembly. So far, everything that actually, one more thing. Let's make the mistake that I was talking about before. Let's do this. Move into RAX, this value, and then do this. So as I've said before, this is a mistake. This is why it's a mistake. Okay, so right here, we're about to clobber RAX with this value from memory. Okay, so now RAX points to FF. And this instruction right here is about to add into memory keyword pointer RAX, RCX, okay? So we're about to write to the location in memory defined by the address FF. And we're about to write the value, whatever's in RCX. Well, currently it's 0, because, I don't know, maybe we should have changed that to RAX. I don't care, it doesn't matter. This is what it is, so we'll just roll with it. We're about to write 0, or add 0 to this location in memory, the FF location in memory. This crashes, like our very first program crashed. Program terminated with signal sig-seg-v segmentation fault. The program no longer exists. Here's why. You might be thinking, why does the location FF not exist in memory? Like, should be a perfectly reasonable location in memory. There's actually a couple reasons why that particular address does not. But the reason is this is our mapped address space. So I did info proc mapping. We're using Linux. We have virtual memory. Doesn't matter for our purposes. You could pretend that this is like physical memory or whatever. In this case, it's just memory. Doesn't really matter. And we have these locations in memory. We have something that goes from here to here. We have something that goes from here to here, here to here. This is start, end, start, end, start, end. These things are my program's code is living in memory somewhere. Is actually what this encodes for. These vvar, VDSO things don't really matter. You can kind of pretend, and vsyscall, we can pretend these things don't exist. They don't really matter. And then we also have the stack. So the stack was what we're visualizing in GDB. This is a small portion of our stack. The fact that it's a stack doesn't matter for our purposes right now. We'll get to the stack later on. This is just some portion of memory. You will see that FF, the address FF, does not fall between any of this start to end business. FF is not mapped. There's nowhere in memory for me to write to. Turns out, like in physical memory, there is like this FF address, like from 0 to hex 1000 as a page of memory. There's like FF, but we don't have access to it, so we're not able to do that. Linux is managing our memory for us, it turns out. And this is as far as our program is concerned, if we try to write to any other location, we're going to crash because that memory is not mapped to us. That segmentation does not exist. It's a segmentation fault. And so we crash. Okay. Actually, and then one more. Well, let's fix this real quick. Or maybe we'll go back to this program real quick, just to go back to the very start of class. Hopefully this instruction now makes sense to you. So we're not doing a keyword pointer, we're doing a byte pointer. I guess I didn't mention, below a word is a byte for these things. There's a byte pointer. You can write 1 byte of memory. And as I said before, 0000, 0 bytes decodes to this instruction. And hopefully you can read this instruction now. We're about to try to use the location in memory defined by RAX and add to the value at that location memory the value defined by AL. RAX is 0, which means AL is 0. We're about to do a null pointer dereference. This is a null pointer dereference. So in the land of C, you've probably inevitably written something like, I mean, it probably didn't look exactly like this, but something like this, right? Where you have a null pointer and suddenly you dereference it. That's a null pointer dereference. That's what's going on here. Now, it just happens to be a null pointer dereference. If we had written this program such that, wait, where did we go? Such that move RAX like 1, right? And then, right, we run this. Now, technically, this is not a null pointer dereference, but it's the same idea. It's a segmentation fault. It's not mapped to us. So that is what happened at the very beginning. And this is why programs often crash if you don't do a clean exit. And we're not going to get to clean exit yet. Turns out there's a whole different world of things to do a clean exit that hopefully we'll get to in the next class. But for our purposes, this is why the program crashes when it runs off. Because more likely than not, sitting in memory is a whole bunch of null bytes. And those null bytes decode for an instruction that is going to do this dereference thing. And if RAX isn't a valid pointer, we're going to crash. And it's going to be really sad. Okay. Cool. So let's go ahead and show off the concept of control flow, right? So far we've dealt with registers, we've dealt with memory. That's kind of like the core of things. Fortunately, a program that just runs linearly, instruction by instruction by instruction, is generally a pretty boring program. If you just wrote a whole bunch of sequential statements in C, probably going to be a pretty boring program. Where programs start to get actually interesting is when we have something like while 1 a plus equals 1, right? Something like this. mean, this program is also unfortunately boring, but it's maybe a step up on the tier of being a not boring program. We have this instruction that will just continuously keep executing. And this is a really important property of programs, the ability for control flow to have a flow to it, to not just be sequential. Alternatively, right, you can imagine something like if A greater than B. I mean, we're not going to get yet into the world. For the same reason that we're not getting to clean exit, we're not yet getting to something like print, or I guess it would be puts, to something that does output. We will get there, but we're not getting there yet for the same reason we're not going to clean exit. Turns out that's the land of syscalls, which aren't too difficult, but that's a whole nother concept. What we're going to do here is we're going to show how we express these concepts that we're used to in C, but instead express it in assembly. So the way that we do that, and I kind of previously showed, like, what if we did move RIP hex 42? Because I already said RIP is the next instruction that's going to execute. As a reminder, that's the program counter. It's the instruction pointer. This does not encode for anything. This is not a valid instruction. Maybe you say, well, like, what, do I need to do this or something? And then that, like, is that going to make it so it decodes? No, that's not going to make it so it decodes. We're still going to get an assembly error there. If we want to express this statement, the way that we do it, and it's the same semantics, I don't know, maybe the assembler should handle this or something. What we're going to do is do jump RAX. So there's a whole bunch of variations of a jump. Right now, hopefully it's clear that what we're about to do is jump to hex 42. Let's go ahead and do that. So we move 42 into RAX. We say jump RAX. Well, yeah, that makes sense. But the tool that I wrote to visualize things for you breaks a little bit because of this. But where we are now attempting to pretend to execute at is at the location in memory hex 42. And what did we say before? In the same way that the address 1 or the address 11 isn't mapped, the address 42 is not mapped, so we crash. This is, if I do like another step, yeah, segmentation fault. This is also a segmentation fault. We didn't even do like a memory dereference, except we did. When you go to decode an instruction, it's pulling that data out of memory and decoding it. This is also doing a memory dereference. It's just doing it even more under the hood. This is a segmentation fault as well. Anytime you access memory in a way that you're not allowed to, you crash with a segmentation fault. Okay, so let's instead jump to, let's do a very boring jump. Well, except it's not going to be. Hold on, let's go ahead and, so my hesitation here real quick is you'll see that this move instruction takes 7 bytes because different immediate values that you put in to RAX decode for different length instructions. I'm gonna make this be a full 8 bytes. Am I? No, I'm not. I think we're gonna be safe here. Ignore that. What we're going to do is put this into RAX. And we'll see whether or not things still line up as expected. But my hope is that I'm going to jump to RAX to this location, which is right here. So this is still, in some sense, executing sequentially. We'll make it not execute sequentially here in a second. But let's see here. Yes. So we put this value into RAX, jump RAX, NOP. So RAX is pointing here. We're about to jump, which, as I said before, it could be thought of as the same thing as move into RIP, the value RAX, and we did not crash. We kind of just sequentially executed, except we didn't sequentially execute it. We aggressively moved the instruction pointer to the place that it otherwise would have gone to anyways. So let's go ahead and do move RBX hex 42. And, you know, rather than like playing this game of like figuring out where this address is, let me just show you how to not do this address manually. We can define another label. So we'll say jump here, or we'll just call it here. So in the same way that we defined underscore start, except we don't have a global on it, we have this thing, just a word with a semicolon, or with a colon, I mean. What we can do, and the syntax is a little bit weird, but the way that we express that we want wherever here is to go into RAX, what we do is we say offset here. So this is going to move that offset into RAX. Okay, and then what we will do is we will jump here and we will do a nop. So assuming that I'm telling the truth about how this is going to work, how I'm saying it's going to work, what should be going through your head right now is that we're expecting to jump over this instruction. So this instruction will not get executed. RBX will not be set to hex 42. We're just going to go straight to here. Okay, it's a good sign. You can see that our disassembler agrees within GDB. It says that we're going to do a jump to 401010. Going way back to the beginning of class. Let's see here. We did this makefile thing. If you're wondering how this address gets resolved, this is what LD is doing here, the linker. This linker is the thing that's responsible for resolving this address. So the assembler does not resolve the address. The linker does, though. So for those wanting the more technical information, the linker is responsible for figuring out that this value goes right here. Okay, so let's step. I guess this move didn't really do anything. I mean, it set RAX. We don't really care about that, though, anymore. Oh, no, we do care. Oh, wait. Interesting. Hold on. This instruction right here, as we wrote before, no, we did write jump here. I see. Hold on. I meant to write jump RAX, and then, so technically it's resolving it here and here. You can do either one. So the fact that I did jump RAX doesn't matter. Yeah, see, it's going to be the same thing. We could get rid of this whole move business, though. If we step instruction, we're expecting to skip past this move RBX hex 42. And so we're going to jump. And guess what? We're here. We're in NOP. RBX never got set. The way my disassembler works is it just shows everything under a label. So we're suddenly in the here land of things. And we jumped past it. So believe it or not, this is very powerful, right? This is control flow. The ability to skip things, and what we're going to show off next is like conditionally skip things. This is one of the most important properties for computer programs to be interesting. It allows it to like respond to something like user input and do something different. Okay, so as we said before, though, we can also do jump here. We don't have to do this offset here business and move it into RAX. This is also totally acceptable. And if we run this, right, the same exact thing is going to happen. And we jump past. Cool. We can jump underscore start. So does anyone have any idea of what this program is going to do? It's, yeah, someone's like doing circles in their head. Exactly. It's going to do, did I write that out in C? Well, no, technically I didn't, but it's going to do this, right? It's just going to spin in a circle. So this program, this is, I guess, a new variant of a program that we've written. In the past, we wrote only programs that will crash themselves. This program will not crash itself. This program will run forever. It will never end. Of course, running under GDB, a debugger, we can kill this process. But under normal circumstances, I'm going to hit C. You haven't seen me hit C before, but C is continue. It's just continuing, and it's going to run forever. This program will never crash. Right now, the CPU is just like burning heat for no reason, wasting, we're we're wasting energy right here. Not too much. Fortunately, CPUs are pretty efficient, especially for something this small of a task. Probably the Linux scheduler is like descheduling this thing, saying stop scheduling this thing. This thing is like spinning CPU cores and doing it, but we're running forever effectively. Okay. Now let's write the following program, right? Probably something that you would write very early on in an intro to CS class. I don't know if it's in Java or C or Python where you write this class in like 110. Let's write the program that says int I equals 0 while I less than 10. We'll create something else. Why are we writing it like this? Obviously, we all know there's better ways to write this program. But we'll do a plus equals 2, right? Let's like write this program. This is going to be involving a condition, right? This is a conditional thing. This isn't going to run forever, especially since we look at this program. I mean, you could write something like this. All right, I don't know, maybe it overflows but it doesn't matter, okay? This thing is gonna happen 10 times. We're going to, I lied. Maybe you caught it. This thing will run forever, right? We forgot the crucial thing of I plus equals 1 here. Let's write this program. And it's very easy to make this mistake, right? I mean, it's kind of a dumb mistake, but it's easy to make the mistake, especially if you're writing assembly for like the first time. You forget like, oh yeah, we need to like increment our loop counter. Otherwise, this thing's gonna run forever. Let's write that program. So what we need to do, let's translate it. So move RAX 0, move RBX 0. So we'll say instead, let's call this RAX, RBX, I don't remember which was which, but let's do this, right? You could write this also in C. It's just maybe it makes it clearer for register's sake what is what. We zero out things. And then what we're going to do is we have our loop here, and we're going to ignore the condition part of it for a second. The very end, what we're going to do is we're going to jump to loop, right? So this is our while forever spin loop. Inside of our loop, we also want to, our bx plus equals 1. While we're in this loop, we also want to add rbx1. And we want to add our ax2, right? So we're incrementing rax by 2, we're incrementing rbx by 1. And now all we're missing is this business, this conditional part of it all, right? Right now, we're just forever incrementing RAX and RBX. If we want to have a done state, so kind of like what happens after here, right? Maybe we put hello world. We're not going to do that in assembly world, but stuff happens after implicitly. Maybe it's just return happens after implicitly. We need to jump to done. We're just going to make that a not for now. The way that we do this, surprisingly simple, though it trips people up, which is fine. It takes some amount of getting used to. But the syntax for this is compare, CMP compare. We want to compare RBX with 10. So I'm going to actually run this as is. We're not there yet all the way. Just because you compare doesn't mean anything's happening. We're going to show what this does. So we initialize, we enter our loop, we compare RBX with 10. So it turns out I'm hiding one of the registers from you. I'm actually hiding, I don't know, like 10, 15 registers from you. They are finite, and there's really not that many of them. If I type info registers, this is all of my registers. So an important one that I've been hiding from you is this thing called eFlags. And I think it's pretty similar to how MIPS does it. You have these flag bits, and these flag bits happen on certain operations. They certainly happen on compares, and they are able to check if we're greater than or not, for example. So just to wrap this up, we only have 2 minutes left in this class. The way that we do this is we say jump if greater than, because we kind of invert this, or I guess jump if greater than or equal to, done. And now if we, and I'm going to set this to 2 here real quick so it steps quicker. We're going to step. We're going to see RAX is now 2, RBX is 1, RAX is 4, RBX is 2, and we're going to do compare RBX with 2. Is RBX currently greater than or equal to, as defined by this comparison instruction? We'll review this again at the start of class tomorrow. As defined by this compare, it's kind of like 2 instructions in one to do this like quasi 1 instruction thing. We did the comparison. Now, if it's greater than or equal to, jump to done. Guess what? 2 is equal to 2, so it's greater than or equal to. We jump to done, and we're out. So this is how we express really this is, a for loop for RBX equals 0, RBX less than 10, RBX plus plus is the same thing, right? Turns out we're just writing assembly though, and we're using the lower level constructs to define these things. This is the same thing as this. Right, just get rid of that. Same thing. Those 2 expressions were the same thing. And that is control flow. So really, turns out you can, minus the syscall part of things, this is how every single program really works. We've really hit the core of it. We're going to continue on, of course, and express some more things and show some more interesting programs. We're going to write the string length program. What is a string? We'll get to that in the next class. And that is all. Thank you all for attending, and good luck.